Welcome my dear students to the video class. We will continue the D and F block element here. Okay, I begin the video with a question. What is or what are transition elements? Transition elements. What are transition elements? Okay, transition elements are the elements having incomplete d-electronic configuration in any of its oxidation state, that is n-1 d 0 to 10 ns1 to 2. They have an electronic configuration but should be incomplete. You know, two or three elements: zinc, cadmium, mercury. What is this? 3d10 4s2, 4d10 5s2, 5d10 6s2. Zinc 2 plus, it is the only one oxidation state, most stable oxidation state. It is 3d10 4d10 5d10. Therefore, in zero oxidation state or in positive oxidation state, their d-electronic configuration is filled. D-electronic configuration is filled. Therefore, by definition, zinc, cadmium, mercury are not transition metals or transition elements. They are not transition elements by definition. By properties also, when we discuss the property, you will see that they are not transition elements. Now, what is an electronic configuration? General electronic configuration, I said to you, n-1 d 1 to 10 ns2 1 to 2. We know that scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Copper, silver, gold, zinc, cadmium, mercury, nickel, palladium, platinum. Niobium, molybdenum, technetium, ruthenium, rhodium. Okay. Now, this is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 36, 38, here 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. 48 plus 6, 48 plus 6, 4, 54 plus 2, 50. Therefore it is 57. Here land right, therefore 57 plus 14. Here 81. 82, 83, 84, 85, 86, 87, 88, 89. Right. Now, what is electronic configuration of, let us take here, this is here for us to complete it. Therefore, D1 S2, D2 S2, D3 S3, here D5 S1, D5 S1. D5 S1, here D5 S2, D5, sorry, D6, D7, D8, here D10 S1, D10 S2. You know why this case and this case? Because it is half filled. Therefore, this happened in all these cases. When you come here, in all these cases, this happened. Here also D5 S1, here also D5 S1. It's a 3D, it's 4D, it's 5D. In all these cases, D5 S1. In all these cases, it happened. Here also D10 S1, here also D10 S1. Therefore, copper, silver and gold, in all cases that happened, chromium, molybdenum, tungsten also this happens. Now, in addition to this, palladium, this is D5, again D5, D6, D7. In palladium, the electronic configuration is very careful. 4D10 5S0. 4D10 5S0. Very careful with this electronic configuration. Palladium. All the electrons. Here, as usual, we expect that D8 S2, D8 and S2. We expect D8 and but that doesn't have this S electron also include also transferred to palladium, and to palladium shows this one. Please careful. Platinum 5D9S1 6S1. Platinum also shows exceptional oxidation state. Therefore, palladium and platinum shows exceptional electronic configuration. Please careful that when we discuss the coordination compound, some special type of coordination compound molecule will be shown by palladium and platinum because of this exceptional electronic configuration. This is all about the electronic configuration. Now, physical properties. First, size. We know that is scandium, titanium, vanadium, chromium, manganese. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. Hafnium, tantalum, rhenium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold. Okay, this is the radius. up to this decreases. Now here almost equal, then increases. Here same radius. Now when you come here, this is here increases, but you when come here equal sign. You know why? Here we have the lanthanides. Therefore, this is 3D series, 4D series, 5D series. Generally speaking, 3D smaller than 4D, almost equal to 5D. Down the group, size increases, but 4D elements have equal size of 5D because of lanthanide contraction. For specifically speaking, lanthanide contraction is happening after the lanthanides. Okay, scandium titanium lanthanum, that doesn't happen. Okay, only from here onwards after the lanthanide. Now along the series, irregular trend up to middle decreases, then equal, then increases. Okay, up to middle size decreases because nuclear charge increases. Because nuclear charge increases. Because nuclear charge increases. In the middle, we can look at in the last size increases slightly because of electronic repulsion of filled electrons. In the middle, what happens? Nuclear charge and electron repulsion counterbalances. That happened here. Okay, this is all about the size of atoms, size of the atom. Okay. Now second, melting point. All have high melting point, all have high melting point at boiling point higher than 1000 degrees centigrade, except mercury, cadmium, and zinc. Mercury melting point is minus 38 degrees centigrade. Cadmium is 728 degrees centigrade. This is 426 degrees centigrade melting point. Okay. Normally, all other elements have more than 1000 degrees centigrade. Highest melting point for tungsten and rhenium. Tungsten is 34110 degrees centigrade. Rhenium 3180 degrees centigrade. That is why tungsten is used in filaments, as I used in incandescent filaments. Okay. Now, the trend of melting point, 3D smaller than 4D smaller than 5D, increases up to middle, then decreases. Okay. One important point, in 3D, manganese show exceptionally low melting point. Therefore, atomic number, melting point, 3D, I am going to 3D, increases up to middle, then decrease. Scandium, titanium, vanadium, chromium, manganese exceptionally low, then as usual decreases as usual. Iron, cobalt, nickel, copper, and zinc. Okay, here zinc. Now our 4D series. This is cadmium, zinc. This is mercury, zinc, cadmium. This is 700 something. This is 400 something. This is minus 80, 38 degrees centigrade. Minus. Okay. Here yttrium, zirconium, niobium. Here molybdenum, technetium, like manganese. Here cadmium. Now, here our tungsten and rhenium. Here our mercury. This is the highest for tungsten and rhenium. This is 5D, this is 4D, and this is 3D. Okay, this is all about the melting point. Now, ionization energy. Energy required to remove an electron from the valence shell. Ionization energy depends upon size, nuclear charge, then electronic configuration. Yes, it has an irregular trend. I'll tell you, first ionization energy of copper is copper, silver, AU are very small. You know why? Because copper, it is 3D10 4s1. Copper, when it releases one electron, it becomes 3D10. Field configuration. Three-D10 has field configuration. Now, similarly, chromium 3D5 4s1. That is, chromium has low first ionization energy. Chromium has also low first ionization energy. And element below the chromium also. Now, zinc, cadmium, mercury has low second ionization energy. What is zinc, cadmium? They have a D10S2 first ionization energy, D10S1. Then second ionization energy you have D10. Because after second ionization energy, a fulfilled configuration will get. Fulfilled configuration. Similarly, manganese and technetium has low second ionization energy. What is their configuration? D5S2. After second ionization, you will have D5. D5S1, D5 only. This is half filled. Okay. Now for after second ionization, you will have half filled configuration. Here after second ionization, you will have a fulfilled configuration. Therefore, they have low second ionization energy. These are very, very important points. Iron has low third ionization energy. What is iron? 3d6 4s2. First ionization 3d6 4s1. Second ionization 3d6. Third ionization 3d5. Therefore, after third ionization, you will have a half-filled configuration. Okay. Similarly, scandium also has low third ionization energy. Yes. Chromium has high second ionization energy. Chromium. Because chromium 3d5 4s1. Chromium plus 3d5. First ionization is low, but second ionization is very high because it's a 3d4. Second ionization happens from half-filled configuration. Manganese also very high third ionization energy, but iron has very low third ionization. Low means when you compare with the third ionization energy of other elements, third ionization energy of iron is low. Low second ionization energy means when you compare with the second ionization energy of other elements, you have lower second ionization energy. Low first ionization energy means when you compare with the first ionization energy of other elements, this element has lower first ionization energy. You never think that low first ionization energy or low second ionization energy means first ionization energy always smaller than second ionization energy, which is always smaller than third ionization energy. Therefore, low second ionization energy doesn't mean that its second ionization energy is lower than first ionization energy. That you never imagine, you never think like that. Low second ionization energy means when you compare the second ionization energies of other element, its second ionization energy is lower. Okay, thank you for watching.